Welcome to AI Shorts, the show where we talk about the intersection of machine learning and product management. In the last episode, we talked about EDA. In this episode, we'll talk about feature engineering, why we do it, what it is, and how to do it. In previous episodes, we've discussed different data types, such as integers, floats, strings, and Boolean. In machine learning, our models are ultimately trained on numbers that are normalized between 0 and 1 or -1 and 1, depending on the model type or the data being used. The process of transforming our raw data to these normalized values is called feature engineering. Model features are used as inputs to the model, and the model uses them to learn patterns to make predictions or classifications. Feature engineering is an integral part to machine learning, and many data scientists spend 25 to 50% of their time developing features. Because it's such an essential part of data science, product managers need to have an understanding of feature engineering to have appreciation for data scientists' work. This will help you discuss feature engineering strategies at the beginning of a data science project. Let's review the three main feature engineering techniques. Categorical encoding is the process of converting categorical variables into a numeric representation that can be used by machine learning algorithms. Categorical encoding is necessary because many machine learning models need numerical input and cannot directly process categorical data. There are several methods for categorical encoding, but the most popular is one-hot encoding, which converts your categorical data into numbers. Using the one-hot encoder class from the scikit-learn library, you can directly perform one-hot encoding in Python. If your data has many categories, one-hot encoding can lead to a high-dimensional feature space, making your data very sparse. There are many ways to deal with this, but one of the most popular techniques is to use PCA, or Principal Component Analysis, to reduce the dimensionality. You can also create a other category for categories that occur infrequently. For numbers, we use feature scaling techniques to scale our values between 0 and 1 or -1 and 1 using normalization or standardization. Normalization scales the value of a feature between 0 and 1. It's appropriate when the data distribution is not Gaussian and the scale of the feature is not meaningful. Normalization is often used for image processing and distance-based algorithms, such as k-nearest neighbor. In Python, you can use the min-max scaler class from the scikit-learn library. Standardization scales the values to have a zero mean and unit variance. It's appropriate when the data distribution is Gaussian and the scale of the feature is meaningful. Standardization is often used for linear and logistic regression and neural networks. In Python, you can use the standard scaler class from the scikit-learn library. There are additional scaling techniques, such as logarithmic scaling, that you can read about online. For some problems, you may consider binning or quantile binning, placing similar numerical values into buckets. Note that some algorithms, such as decision trees and random forests, are not affected by the scale of the features, so we generally don't scale in those instances. Text feature engineering is an important part of natural language processing and can significantly impact model performance. Here are some of the most popular text feature engineering techniques. Bag of words is a simple and popular technique for text feature engineering. It represents the text as a sparse matrix of word counts. Bag of words is appropriate when you have a large vocabulary and the order of the words is not important. TF-IDF is a technique that assigns a weight to each word in a document. The weight of the word is based on its frequency in the document and the inverse of its frequency in the corpus. TF-IDF is appropriate when you want to downweight common words and upweight rare words. Lowercase transformation makes all words lowercase. Removing punctuation is exactly what it sounds like. We're removing the punctuation. Word embeddings are dense vector representation of words that capture semantic and syntactic information. Word embeddings are appropriate when you want to capture the meaning of the words and the relationships between them. Word embeddings are often used in NLP tasks such as sentiment analysis, machine translation, and named entity recognition. N-grams are sequences of n-contiguous words in a text. N-grams are appropriate when you want to capture the context of the words and the relationships between them. N-grams are often used in sentiment analysis and text classification tasks. Cartesian products create a new feature by combining two or more text or categorical values. These can be useful for recommendation engines. There are more interesting text feature engineering techniques out there, and I encourage you to discover them on your own. The difficulty with feature engineering is that there's no formula or hard rules to follow. It's as much an art form as a science, and the features you create can dramatically impact the performance of your model. This is why I find this to be one of the most exciting areas of machine learning. Having a deep understanding of feature engineering can help you as a product manager have rich conversations with your data science team on different approaches to create your model. I hope you enjoyed the video on feature engineering, and I'll see you next time.